So let's take a look at section 5.5. This is our last section that we're going to be doing stuff in 2 dimensions. Tomorrow we're going to look at 3D. And today we're going to look at a product. Now, if you're thinking, well, didn't we already do product? You know, something like this, 2 times v. Yeah, that's called a scalar product. Remember, when you scale a vector, it just makes the vector longer, shorter, or it can flip the direction. But this is a number times a vector. What we're going to look at today is a vector times a vector. All right? So multiplying 2 vectors together. All right, so what I did is I wrote down 2 vectors in unit vector notation. Vector v has a horizontal component of a1 and a vertical component of b1. Those would be like your numbers, like 2i plus 3j. Vector w, it's also got a horizontal component, that's a2, and a vertical component, b2. It could be like 5i minus 6j, something like that. And these are all vectors, so again, remember, these are all bold. Okay, if you're not sure where the I and j come from, that's probably because you weren't here yesterday. And that's what we talked about yesterday. So a1, a2, b1, b2. Those would all be numbers in a problem. We're going to do one with all numbers in a minute. So the first thing we're going to find between these 2 vectors is called the dot product. And first thing I'm going to show you is how you write that down. Like, what would it look like on paper? Like, if you were writing dot product. It would look like that. And the way you pronounce that is v dot w. You don't say times. The reason you don't say times is because when we deal with vectors, you've got what's called a dot product, and you also have what's called a cross product. Multiplying vectors, there's 2 ways to do it. We're learning the dot product today. We can't do cross product today. The reason is because cross product is only something that works in 3D. It's impossible. You can cross product that doesn't exist in 2D. So tomorrow when we look at 3D vectors, that's going to be the one new thing we look at in 3D that we've never looked at in 2D, a cross product. Okay, but for today, dot product, v dot w. Okay. Very easy to find a dot product. To find a dot product, you take the horizontal component of the first vector and the horizontal component of the second vector, and you multiply them. a1 times a2. Plus, take the vertical component of the first vector, take the vertical component of the second vector, and multiply those together. And that's how you find a dot product. So let's look at what the answer would be. Okay. What did I say earlier? A1, A2, B1, and B2 are all what?
Numbers.
They're all numbers. What do you get if you multiply a number times another number?
You get another number.
You get a number. If you multiply a number times another number, you get
A number.
a number. And what if you add a number to a number?
A number.
A number. So when you do the dot product, the answer is a number, like 7 or 12. That number means something. We're going to look at what it means later. All right. So if you multiply 2 vectors and you use a dot product, the answer is a number. If you multiply 2 vectors and do a cross product, we'll see what that is tomorrow. Okay, but they're 2 totally different things. Okay, so let's find the dot product between these 2 vectors. 2i minus 3j and 5i plus 3j. Okay, what I usually do first is I just write down something like this. And then I fill in all the values. Right, so Joe, what's the number that's going to be in the first parenthesis?
2.
Yep, 2. And Kiara, what's going to be the number in the second parenthesis?
Oh, 5.
Yep, 5. Okay, so we'll do that in a second. Christian, how about the number that's in the third set of parentheses?
3.
We got
-3.
Yeah, -3. And then the fourth number, that's your 3. So we did this times this plus that times that in exactly the order that I circled them. Okay, so let's see what we get. Ephraim, 2 times 5 gives me 10. And Eric, -3 times +3.
-9.
So that gives me 10 plus -9, which is 1. Okay, so the dot product between those two vectors is 1. And that's it. That's the dot
That's how
product.
easy that is.
Yep. So with the dot product,
Is it going to stay that easy?
we use the dot product to do something else. I'm going to show you what we use it for.
Exactly.
Even what we use it for, it's not that hard. Let's try this. W dot V. All right. Well, let's see. That's the point. I want to see what happens if you switch the order.
It comes out the same thing.
You think it's going to be the same?
I know it's going to be the same.
It's gonna flip, so it's.
5 times 2 is the exact same number.
No, not like that.
All right. So Joe just said we're going to start out with 5 times 2. He's right because you're starting with W first and then V. So W is 5, V is 2. What number would go in the first parenthesis here?
3 and -3.
3 and -3. But what's 5 times 2?
10
10, and 3 times -3?
is -9.
It's still -9. So the answer here is still 1. What does that mean about the dot product?
So doesn't matter which way.
It doesn't matter which way you multiply it, and there's a name for that. You can switch the order and it doesn't affect the answer. And remember the name of that property? Yep. Not associative, but you're very close. It's another property we usually study when we talk about that one. What's the other property we mentioned? Begins with a C. Commutative. So what this means is that the dot product is commutative. V dot W is the same as W dot V. Now, when we study cross product, that's not going to be true. If you do V cross W and then do W cross V, you don't get the same answer. So that's going to probably be one of the first times you've ever done something with multiplication and the order matters. Most of the time, order doesn't matter with multiplication. When we learn cross product, it does. Okay. But for today, it doesn't. Okay, let's find V dot V. So we're dotting a vector with itself. V dot V. So I'm just going to write down everything. I'm going to make it smaller so we can maybe see V. Oh, no, I'm going to have to scroll up.
2y minus 3i.
So I have a question. If you had V squared, would it be V dot V, or would you never see that?
You wouldn't see that because that's kind of vague.
Okay.
You wouldn't see something like that as a vector. Yeah, because you wouldn't know. Yep, that's a good question. All right, so when I do V dot V, what am I going to fill in the first set of parentheses?
2 times
2
2.
times 2.
And then -3 times -3.
2 times 2, -3 times -3. So we get 13. Yeah.
Where did the 2 and the -3?
2,
Oh,
-3. It's just like they're the same vector twice. So it's a 2 and a 2 and a -3 and a -3. Now, what is that called when you do something times itself in multiplication? Squared. So this is like 2 squared plus negative 3 squared. Does anybody remember what calculation we did and that was part of it? You squared something, but then you also had to do something else. Yep?
Well, the Pythagorean theorem.
It was like the Pythagorean Theorem. So what do we use that for? We use Pythagorean Theorem when you're trying to find the what of a vector. Not the hypotenuse of the vector. Vectors don't have really a hypotenuse. What do we use the Pythagorean Theorem for? What are you trying to find when you want that?
Is that the length of the vector?
It's the length of the vector, the magnitude. So, to do Pythagorean Theorem, you square something else, you add them up, and then you take the square root. Well, the only thing we didn't do here was take the square root, and you're not supposed to. We squared something else, and we added them up, and we just wrote that number. So what I'm trying to show you here is when you dot a vector with itself, it's almost like you're finding the length of it, except you're not really taking the square root. Okay? Let's try and see if that works again with W. What would I do for W dot W? 5 times 5. Can you say it again?
It would be 3 times 3.
We're missing something. Got a question?
Be 5 squared plus 3 squared.
Plus, yeah. I'm looking for the plus in the middle. If you said 5 squared or 5 times 5, I don't care which way you say that part. But please hold. All right, so W dot W. Joe, can you just say it again?
5 squared plus 3 squared.
5 squared plus 3 squared. So it's almost like you're finding the length. 5 squared plus 3 squared, but then you stop. You don't actually take the square root. So 25 plus 9 is 34. So that number is not the length. It's really what? It's the length without the square root. So what does that mean?
Squared.
Squared. That's the length squared. If you took the square root of it, it would be the length. So if you dot a vector with itself, you don't get the length. You get something close to the length. You get the length squared. Okay? And take it's writing the same thing twice. So dotting a vector with itself gives you the length of the vector squared. Okay, let's set up this one. So I'm doing the dot product. Can someone tell me what are the first 2 things I would multiply together? 2 times 0. So 2 times 0. And what comes after that? Plus. Plus what, Joe?
6 times 0.
6 times 0. And what's the answer? Now, can somebody be more specific about that? Like 0. Describe that a little more.
Nothing.
I want to be a little more specific. Like when we do a dot product,
Like a label?
kind of like a label, but when you do a dot product, what kind of answer do you always get?
A number.
A number. So that's 0, the number. So should I make it bold? No, don't make it bold. If you did something like this, that's wrong. Okay? So I just want you to understand that when you do a dot product, the answer is a number, not a vector. Okay? If you wanted to get an answer like that, that would come from doing something like this. 0 times a vector. When you multiply a vector by 0 with a scalar product, the answer is the zero vector. Because when you scale a vector, the answer is always a new vector. Okay? But when you do a dot product, the answer is always a number. All right, so the dot product is distributive. So we've learned in the past, if you've got something on the outside and then something on the inside of parentheses that's addition or subtraction, you can go like this. Well, you can't assume that you can do that with the dot product, unless you know you can. And you can. Okay, so you can do distributive property with the dot product. U dot V plus U dot W. Just don't pronounce this as times. Pronounce it as dot, because that's what it is, dot product. Okay, so I might ask you something like that on the test, like is the dot product distributive? And then once we learn cross product, I might say is the cross product distributive? You know, maybe one is, maybe one isn't. I don't know. We'll learn tomorrow.
What are you so vague about the cross?
About the cross product? Well, if I tell you everything today, you won't tune in tomorrow. I gotta keep you coming in. It's like a cliffhanger, right? It's like I gotta find out about the cross product. So to find the angle between two vectors, that's basically what the dot product is used for. So you got two vectors like this, and you want to know what's the angle between them. That's where we use the dot product. All right, so I'm going to give you the formula. It's a very straightforward formula. Now, if you didn't have the formula that I'm about to give you, let's just say you had something like this. You've got a grid, and you've got a vector that goes like that, and a vector that goes like that. Technically, you should be able to find that angle. How could you find the angle here if I didn't give you the formula I'm about to give you? What do you think you'd have to do first in that diagram? We do this a lot when we do stuff with trig. Any thought? Yeah?
You could draw a circle.
Okay, we do use circles a lot, like for unit circle stuff. This one we're not going to use a circle for. But that's a good guess. We're not going to make a circle out of that. We are going to make something else out of it.
Triangle.
All right, how would I make a triangle out of it?
Sounds good.
How?
I think you said, how about I
Well, how would I make the triangle? Like, what would I have to do?
connect with you?
Yeah, just connect the side that's missing. All right?
Sounds good.
Now I've got a triangle. What could I find out about that triangle? You don't even need trig to do it. You could do this in geometry.
The bottom line.
Okay, you could find the bottom. That one's easy, because you could just count. Now, could you find the length from here to here?
A little bit above 3.
Not really.
You can't find that?
You could do like that like 1, 3 thing, right?
So
Don't you make another triangle?
you could make another triangle, but you don't even need to do that. Isn't there a distance formula in geometry? Find the distance between 2 points. Remember, does this look familiar? x2 minus x1
Midpoint formula, right?
We're gonna do all that work to find one.
plus y2 minus y1. Does that look familiar? The distance formula from geometry?
Oh, yeah, you'd be better off just making another.
You could make another triangle. That's exactly what the distance formula is. You're right. You could make another triangle right here and say this side is 1, this side is 3, and then use the what? Just use the Pythagorean Theorem, and there's that side. Okay? So, I'm not going to go through it, but if I wanted, I could definitely find the length of that side. Okay? Same thing here. If I wanted, I could find the length of that side. And then, if you know all the sides in the triangle, that's a side, side, side triangle. If you know every side. There was a law we studied a couple weeks back that if you know all the sides in the triangle, you can find the angles. Anyone remember the name of that law? Spent a whole weekend? Well, it's the law you use to solve a side, side, side triangle.
gonna tell us he wants to look it up.
I'm hoping somebody gets it. It's the law.
The law of sines.
It's not the law of sines, it's the other one.
Cosines.
Law of cosines. So if you didn't have the formula that I'm about to give you, you can find the length of each side, and then once you know all the sides in a triangle, you can find any angle you want using law of cosines. So you can do it. It's a lot of work, right? It's going to take, for me to find the distance of all these sides and then use the law of cosines, even knowing exactly what I'm doing, it's probably going to take me about 3 or 4 minutes to just go through all those calculations. If you don't know what you're doing, even longer. Using the formula that I'm about to show you, we can find the angle much quicker. Now, this formula is based on the law of cosines. So what trig function do you think is going to be in it? Don't think too hard.
Cosine?
Cosine. It's based on the law of cosines, so it's going to have a cosine in it. It's basically going to do all the work I just described here for you automatically, without you having to do it. So that's the formula to find the angle between two vectors. You have to find 3 things. 3 things we've already done. The dot product, the length of u, and the length of v. So the cosine of your angle is the dot product over the product of the 2 magnitudes. I don't think you need to write what's in parentheses as long as you know what the double bar symbol means. The denominator is the length of u times length of v. Okay, so that saves a lot of time, having to do the distance formula 3 times to get all the sides, and then plugging everything into law of cosines. A lot less calculations with this formula. Okay, so let's look at an example. So we've got the vectors 4i minus 3j and 2i plus 5j. Let me sketch them real quick, just kind of get an idea of maybe what we think the angle should be. So the first one is right 4, down 3. So let me start here. Right 4, down 3. Looks like that. The next one is right 2 and up 5. Right 2, up 5. So if I put those together, it's not perfect, but what does it look like that angle is close to? Yeah, again, I didn't draw it perfect, but I'm going to guess the angle is somewhere between 80 and 100 degrees. It's kind of close to 90, it looks like. Maybe it's a little bigger, maybe it's a little smaller. But it's probably around 80 to 100 degrees. Let's figure it out. So let's find the angle between u and v. First thing I need is the numerator. That's my dot product. Okay. What's going to be the calculation for my dot product?
Four times 2
4 times 2, yep,
plus 3 times 5.
plus
Negative 3 times.
negative 3 times 5, which is negative 15. And my dot product, if I add those up, what do I get? Negative 7. Okay, there's the first thing. There's your dot product. Next thing, I need the magnitude of u. All right. What's the calculation to get the magnitude of u? What do we want to start out with? I usually say to write this down so you don't forget it. Yep.
The square root.
So you got the square root. Yep. And what goes under the square root?
4 squared
Yep.
plus 3 squared. Negative 3 squared.
Negative 3 squared.
Doesn't really matter.
It doesn't really matter because you're going to square it. 16 plus 9 is 25. Square root of 25 is 5. So we got a nice answer. We might-
I remember that by now.
Yep. And now let's find the length of v. What's that calculation going to be?
2 squared plus 5 squared.
2 squared plus 5 squared. That's 4 plus 25, which is how much?
29.
Square root of 29. Okay, so now we've got all three things. Let's fill them in. So cosine of the angle equals dot product, where is it? Dot product goes on top, the magnitudes go on the bottom. Dot product is -7. Magnitudes go on the bottom. 5 square root 29. Now, I want to get theta by itself. I don't want cosine there. So how do we get rid of cosine?
Divide by cosine.
Remember, cosine's a function, so you can't do arithmetic with a function.
Inverse cosine?
Yep, we're going to take the inverse cosine. So take the inverse cosine of what's on the left, inverse cosine of what's on the right, and let's see if we get an angle that's kind of close to 90. If you're doing degrees. So let's do it in degrees. So second inverse cosine, -7 divided by 5 square root 29.
Wait, why'd you have to do the inverse?
To get rid of the cosine on the left. So I'm going to close the parenthesis for my denominator, close the parenthesis for your inverse trig. And yeah, I didn't draw it perfect, but we thought it was kind of close to 90. That's a little bigger than 90, not a lot, but a little bit. So it should be about 105.0. Oh yeah, we could say 105.1. Touch the board as I was writing. So that's how you find the angle between two vectors. 105.1 degrees. Any questions on that one? So, I think this is the only new vocabulary word in the, well, dot product was a new word too, but orthogonal is the other new word in this section. Orthogonal just means perpendicular. Okay, some people get kind of technical, but for our purposes, really perpendicular and orthogonal are synonyms. Just another way of saying the same thing. So, if they ask you, are the following two vectors orthogonal, you're checking to see that the angle between them is what? 90, exactly. You're checking to see if the angle is 90. That's all. Now, there's actually a shortcut to check if the angle is, how much did we just say? 90. Let's say that the angle came out to 90. So you'd have something like this. You'd have a dot product on the top, and you'd have two magnitudes on the bottom, but somehow you do that all out, and they come out to 90-degree angle. Well, let's see what the cosine of 90 is. It's 0, right? So if the angle between them is 90, what that means when you take the cosine of 90 is you get 0. So the only way that two vectors can come out to be orthogonal is when you do this side out, you get an answer of 0. How can a fraction ever come out to 0?
Put a 0 on the bottom. No, on the top.
equally
On the top.
Yeah, if you divide by 0, we can't do that. So where else? On the top. If the top of your fraction comes out to 0, that's going to force the left-hand side to be 0, which means the angle is 90. So my question is, what's in the top of the fraction?
0.
Well, it would be a 0, but in our formula, what goes there? The dot product. So that's the whole key. If the dot product comes out to 0, then your vectors are perpendicular, because it would make the whole fraction 0, which makes the other side 0, which means it had to be 90 degrees. So technically, you don't even have to find the lengths. If you do the dot product and it's 0, you're done. The vectors are automatically perpendicular. And that's the symbol for perpendicular, if you don't remember from geometry. So let's find the dot product between these two vectors and see if they are perpendicular or not. Okay, what's going to be my calculation to find the dot product? Yep. 2 times 1. Remember, there's a 1 in front of a letter if you don't see it. Plus what?
1 plus 2.
2 times 1 times 1 plus 2?
J times 2J.
It's just 2.
Oh, no.
1 plus, no, 1 times 2.
1 times 2. 2 times
I
1.
was saying plus this whole
You
time.
were
Oh,
saying plus, yeah.
My bad.
So 2 times 1 plus 1 times 2. What's the dot product? 4. Are they perpendicular? No. What could you change there to make them perpendicular?
If you move the 2 over to the J.
Um,
Like if I in V was 1 and then J in V was 2.
So if you did that,
Yeah.
then you'd have 1 times 1, which is 1, plus 2 times 2, which is 4. So now the dot product would be 5.
My bad.
But it's all right, we tried something. It's actually even simpler.
Oh, you put a negative.
Just put a negative anywhere. If you make any one of those 4 numbers a negative, then you'd have 0. Doesn't matter which one. Okay. But the way they are now, no, they're not perpendicular. We already did that. All right. So parallel, there really isn't a shortcut for parallel. You pretty much have to do the whole problem out. But there's 2 situations where vectors could be parallel. Those vectors are parallel. And those vectors are parallel. They're both parallel. So the difference is one of them has an angle, like if you line them up, that has an angle, well, I can't move them. But one of them has an angle of 0 degrees because they both point the same way, and one of them has an angle of 180. You could think like, if you just took this vector and moved it down here, there's a 180-degree angle. And if you took this vector and just put it on top of the other one, that's a 0-degree angle. Right? So 2 vectors that are 0 degrees or 180 degrees are parallel. Okay, so let's try this and see if the vectors come out parallel. So we kind of got to go through the whole thing. You got to do the dot product, you got to do the magnitudes, you got to do the whole problem. Unless the dot product comes out 0, because then if the dot product comes out 0, we know they're what?
Perpendicular.
Then they're perpendicular, they can't be parallel. Then we can stop. Right? So dot product, 4 times 20 plus -5 times -25. That's 125. So my dot product is how much?
205.
205. All right, so they're definitely not perpendicular. The length of V, it's the square root of 16 plus 25. 4 squared, -5 squared. 16 and 25 is how much?
41.
Yep. Square root of 41. And the length of W, 20 squared is 400. -25 squared is 625. 25 times 25. So that's the square root of how much? 1,025. Okay, so let's plug it into the formula and see if the angle is 0 or 180. Cosine of my angle, what goes on the top?
$205.
Yep, dot product. And on the bottom, the product of the magnitudes. Now, this is the case where Joe had mentioned you could do 41 times 125, 1,025, but I'll just keep them separate because I'm just going to type it all in. So let's do the bottom first. It'll be less to type in all at once. Square root of 41 times square root of 1,025 is 205. So the bottom is 205. The top is 205. So what is that fraction on the right side?
0.
1. Right? 205 divided by 205 is 1. So now we need the what? to get theta by itself?
Inverse cosine.
Inverse cosine of 1, I get an angle of 0. Now the question didn't say find the angle. The question said, are they parallel? Yes or no? The answer is yes. Why are they parallel? Because the angle is 0. Any questions on that one? Right, so those are the two special cases of parallel of angles between vectors: parallel vectors and orthogonal vectors. Make sure you remember that word, orthogonal. All right. So last thing we're going to look at is the word problem. An anomaly. All right. So this problem, just to kind of set it up, is going to be about a plane flying, and there's going to be a wind. And I basically want to know what the effect of the wind is going to be on the plane. There's two things that it would affect. The wind could speed the plane up or slow it down. And what else could the wind do to the plane?
Fuel efficiency.
Okay, yes, it does tie in with fuel efficiency. But even more basic. If wind is blowing, the plane could what? Could move. It could go in a different direction, right? So if the wind is blowing, it could go in a different direction. So we have a plane that maintains an airspeed of 500 miles per hour due south. Now, important thing I have to explain is the difference between airspeed and ground speed. People know the difference? Okay, imagine that there's no wind. Okay, just to make this simple. You're driving in your car. It's a day that if you were standing still, you don't feel any wind. All right, you put your window down, you put your hand out the window. Let's say your speedometer says you're going 40 miles an hour. Your hand's out the window. Don't do that, it's dangerous. But your hand's out the window. How fast is the wind hitting your hand?
45.
Your car is going 40 miles an hour. That's what the speedometer says. The wind is hitting your hand at 40 miles an hour. Okay. So now, let's say that you're driving into the wind. Let's say that there's a 20 mile an hour wind blowing at your car. You're driving right into the wind. You put your hand out the window. Okay, your speedometer says you're going 40. How fast is the wind hitting your hand?
60.
60. Because the car is moving at 40, the wind is blowing at 20. It's hitting your hand faster. So that's the same idea here. Airspeed is if a person put their hand outside the window, how fast is the wind hitting their hand? Ground speed is if you had a radar gun and you could measure the speed of the plane from the ground, how fast does it look like it's moving in the sky, right? Which can be very different than the wind blowing over it. So airspeed is 500 miles an hour. The wind, which we're calling the jet stream, is 80 miles an hour. Now the direction of the jet stream is northeast.
Wait, so the jet stream is what you count as the wind that's already there?
That's the wind that's blowing, yep. And we're going to assume that it never changes. It's just going to be the same direction, same speed. The wind's pretty constant. Is the wind helping the plane, or is it going to slow it down?
Slow it down.
It's going to slow it down. The plane's trying to go south. The wind is blowing northeast. So the plane isn't flying directly into the wind, but it's kind of hitting the wind at an angle, right? But it's not a tailwind. It's more of a headwind. It's slowing it down. We're not going to do both of these. We're just going to find the direction of the. Which one do we want to do? You know what? As we're going through it, whichever one I get to first, that's the one I'm going to stop at. I'm not sure if we're going to get to the speed first or the direction. I think we're going to get to the speed first. So I think that's what we're going to end up finding. Yeah. Let's just find the actual speed of the airplane. And that's it. A lot of information there. The best thing to do would be to sketch that out. All right, so let's make a sketch. So the first thing I'm going to do is I'm going to draw a vector that represents the airplane. What direction is the airplane going? South. So for our purposes, I'm going to have that be down on the board. Okay, south is down. So, all right, let's do this one in red. This is not to scale, right? But that represents the plane. So let's call this the vector for the plane, v sub p. Now, the wind is blowing which direction? North, east. Exactly between north and east. Well, again, north, east. So it's like a 45-degree angle, basically. All right? So here's the direction, and it's blowing at 80 miles an hour. Again, that's not to scale, but it's a smaller arrow than the plane, because the plane is going 500. So that's your, we'll call that our vector for the wind, v sub w. What I want to find is the actual speed of the plane. So the way you could think of it, if just for a second, don't copy this part, but just go like this. Put that vector on the end and draw this in. That vector in black, the length of it, represents the actual speed of the plane. Does that vector in black look longer or shorter than v sub p? It's shorter because it's flying into the wind, it's slowing it down. So we'll call this v sub a, the actual velocity vector. So we have a vector for the wind, a vector for the plane, and then the actual vector is when you combine the wind and the plane together.
Should we draw that in that?
What's that?
Should we draw that the actual speed in that?
You can draw it if you want. You don't really need the v sub a. But the idea is, what you do need is this. The actual vector for the plane is a combination of what the plane thinks it's doing and what the wind is doing to it. That's what we have to figure out. So the actual speed is a combination of the plane and the wind added together. All right, so let's find, let's start with v sub p. Just as a reminder of our velocity vector, okay, we have to convert these two things to velocity vectors. This is the formula from yesterday. It's the magnitude, and then cosine of your angle, I, plus sine of your angle, j. That's the formula for a velocity vector. Okay, so let's fill in what we know about the plane. Let's start with the magnitude of the plane. How fast does the plane think it's going? 500 miles an hour. In what direction? South. Now we can't plug south in as an angle. We need an angle that represents south. When we go straight down, what angle is that? That's 270. If you know about compass headings, that's different, don't confuse it. But in our purposes, 270 means south. Yeah?
Can you slow down a little? What angle is that for in the formula?
That angle is basically this angle right here. We're doing the velocity vector for the plane, and v sub p points straight down. That's an angle of 90, 180, I'm sorry, 0, 90, 180, 270. So v sub p is straight down.
So it's whatever direction the arrow's pointing.
It's whatever direction the arrow is pointing. We're going to need the direction for the wind in a second, too.
So it's like what we did at the beginning of the year?
We did it yesterday.
Yeah, but
We might have done a little bit. Yeah, we did a little bit at the beginning of the year, too. Yeah.
Wait, what's that say after the plus?
After the plus, sine.
So sine?
All right. So cosine of my angle, I, plus sine of my angle, j. So we just converted the information about the plane into a vector. That's what we need. We need it vectorized. Okay. So we vectorized it. Now, let's do out the distributive property. 500 times cosine 270. 500 cosine 270. All right. That gives me 0. The I is which component? Left and right or up and down? It's the left and right, which makes sense because the plane doesn't think it's going left or right. It's going straight up or down, in this case down. So there is no left and right component. It's straight down. Plus, let's do that one. 500 sine 270. Negative 500. Now negative makes perfect sense because j is your vertical. We're going down. So the speed of the plane as a vector is negative 500j. That's v sub p. That's the vector for the plane. Now let's find the vector for the wind. How fast is the wind blowing?
80 miles an hour.
80 miles an hour. So put that on the outside. And we're going to need cosine of my angle I, sine of my angle j. But now I need my angle. It says the wind is blowing northeast. Northeast isn't an angle, that's a direction. That's a 45. North and east, east is 0, north is 90, northeast is right between the two. So there's your angle. Anyway, so let's see where we get there. So 80 cosine 45, and then we're going to do 80 sine 45. They come out exactly the same. And it should, because the wind is blowing exactly the same amount east as it is up. So basically, it's like 56 miles an hour east, 56 miles an hour up, and that gives you a wind 80 degrees northeast. That's what's happening. So let's write down these numbers, 56.7. So 56.7i plus 56.7j. There's your vector for the plane. There's your vector for the wind. How do we get the actual vector? What do we have to do with the plane and the wind? Yeah? Combine them. Combine the plane and the wind together. So, when I combine them, does the plane have an I component to combine with the I of the wind? 0. So 56.7i, that part stays the same. Does the wind have a j component to combine with the j component of the wind? I mean, does the plane and the wind both have j components?
Yeah.
Yes, they do. One of them is negative 500. The other one is 56.7. That changes my j component to negative 443.3. Now, that's the vector that represents what's actually going to happen to the plane. I said, let's just find one thing. Let's find the speed. That means I want to know, if you draw that on paper, how long would it be? Okay, so when I find the length, what's the first thing I do? First thing you always write down.
Oh, you write the square root.
Write the square root symbol. Yep. And what's the first number that I square?
56.7.
56.7. It's kind of big, but we're just going to use a calculator. And the second number?
Negative 443.
Yep. So let's see what the actual speed of the plane is. What was the speed of the plane? What was the airspeed? 500. But the wind is going to slow it down, so somebody with a radar gun on the ground is going to measure the speed we're about to find out. So it's the square root of 56.7 squared plus negative 443.3 squared. So somebody with a radar gun is going to get that the plane just warped into another dimension. I need parentheses. Anytime you put in a negative, you got to put parentheses. Now we should be good. So from somebody observing on the ground, the plane isn't going 500 miles an hour. It's going about 446.9. About. Okay? So the way you have to do it every time is think of this formula and then set up your wind as a velocity vector and the plane as a velocity vector and add the two together. And that gives you this. Then you can find the speed of that just using your square root. Okay. So I think that application, I think that's a little easier than the cable's hanging, because that cable's hanging, that has a lot of steps. This one's not as easy as like the first one we did yesterday, but I still don't think it's as hard as the tension in the cables. But still have to know what you're doing. All right. Okay, so on 352, each question has 3 parts. Okay, part A is find the dot product. This is all in the book. Part B is find the angle. And then part C is, are the vectors parallel, perpendicular, or neither? So it's not like it's 3 separate parts. You've got to do all the parts to do part C anyway. So find the dot product, which will help you find the angle in part B, which will then help you tell me if they're parallel, perpendicular.
What about 25? Does 25 have 3 parts?
25 does not. That's an airplane problem.
Alright.
It's about an airplane flying in the wind. It's just a different speed wind and a different direction plane. Yep.
Same problem we just did though?
It's exactly the same problem we just did with different numbers. So, same steps. Yes.
Can you just go back to that last slide?
Yep.